Alright, in this next step we want to get the primary displacement, that is the displacement caused by the actual load on this reduced or relaxed system. And remember, we removed the reaction out here, the vertical reaction out at A, so that's the displacement that we have to go develop. Now we go look at the moment diagram that comes from this actual load in this specific situation. It creates curvature only in a small portion of the structure, so that actually makes the drawing a little bit easier to go create. When you do these, don't get too exaggerated as you do things, but you have to comply with all the requirements of this things of moment curvature, boundary conditions, no rotation, no translation down here at the base. We've got no curvature up at the top half of that beam, so that top portion just goes along as a straight line. We don't allow the column to shorten, so that means that the top of the column just slides directly over, right? And so that will later be a useful thing to have determined. It is the displacement at B in the relaxed system with no redundant reaction out there. It is in the X direction, so we'll put that little subscript on there too. Right, now that joint has rotated. It's displaced sideways and it has rotated. There's an extended tangent, so that would be theta at B in the system that doesn't have the redundant reaction. And when we create the right angle, reconstruct how that joint is, and put a new not undisplaced but undeflected but rotated and translated portion of the beam, right? No curvature, so it's a straight line. This angle over here is the same as up there, and that's critical because when we want to go and find out how much did this joint move downwards, that's what we're actually after. That is delta A0 in the y direction. That's what we're really trying to achieve or calculate. Now also note, because of no shortening of the member, then A has moved to the left by the same amount that B moved to the left in this specific instance, right? And then basic geometry, if the joint rotated by theta B0 over here, then it rotates by theta B0 there as well. That tells us strategically then that the value that we're seeking initially here, delta A0, is just going to be equal to this right triangle relationship. Opposite over adjacent is tangent, and since it's small angles, then tangent of theta B0 is about the same, so theta B0 times that length of that member is going to be all we have there, and that's going to be 12 feet. That's the length of our member times theta B0, which we can go find back over here. And then we note that theta B0 is, alright, so it's this angle, it's also that angle, and it's this angle that represents the top of the column. And then so theta B0 is going to be the same as the relative angle change that happens between two tangents drawn to the elastic deflected shape. Way down in here, that's theta B with respect to a tangent drawn at not A, but rather C, because that's what C is. C's down here. And so those two are the same, and that's given to us by the first moment area theorem, that's equal to the area under the M over EI diagram between those 2 points. So that's 60 foot over EI times, well, that's 6 foot high, so that's 360 divided by 2, so 180 kip foot squared over EI for the value of theta B0. And that means that delta A0 y would be equal to 12 feet times 180 kip foot squared over EI, and that would be 12 times 180, or 2160 kip foot cubed over EI going downwards. We're not going to worry about the positive negative aspect of it. Let's just get it the way it's physically acting. Now, because it's going to be useful later for us, and I'm going to look ahead, I'm going to go ahead and calculate delta B0x as well, and note that it's going to be equal to the tangential deviation of point B with respect to C in this specific case. So that's equal to, once again, that area 1/2 of the 60 kip foot over EI times the height, 6 feet, that's the area, times the moment arm, and that moment arm is 2 foot off the base, 4 foot there, and then 6 foot up to there. So the moment arm that I really want is that 10 foot. So 60 times 60 is 3600 over 2 is 100, or 1800 kip foot cubed over EI, and that's going to be acting to the left as shown. Again, that's going to be a useful number for us later on.